Okay, so here we're just going to briefly talk about how to calculate the inverse of a 2 by 2 matrix. And basically, at the end of this, there's going to be a formula, and I just recommend that you memorize the formula. But just so you can see where the formula comes from, it's pretty simple. So first of all, just let's recall the definition that a matrix is invertible if there is some other matrix B such that when you do matrix multiplication, you get the identity matrix. And we've already proved that if such a matrix exists, it's the unique, and so this is the notation for what the inverse is. Okay, so here is our particular case. So you imagine that you're given some matrix A. So that means we know little a, little b, little c. Those are explicitly given to us. And our goal is to find its inverse matrix, which for the moment we'll just call capital B. And so has to be a 2 by 2 matrix. So I'll just call it matrix B. I'll call the entries x, y, z, w. We need well, for them to be inverses, we need, when we multiply them, to get the 2 by 2 identity matrix. So this is the condition that must be satisfied. And so if we expand that out, that's happening on the subsequent line. This is our matrix A here. This is our matrix B here. If we just multiply them out using matrix multiplication, that's what we get. And this is what we want or need in order for the two matrices A and B to actually be inverses of one another. And this is actually sufficient in order to figure out a formula. So how do we do that? Well, the condition we need right here actually just gives us a system of equations. Actually gives us two systems of equations. If we just compare the first column, so if we compare the first column, we see that we need ax plus bz to equal 1, and we need cx plus dz to equal 0. And remember, we're assuming that we know A and B and C and D. So the variables here that we are trying to find are x and z. So we want to find x and z in terms of A, B, C, and D. And here I won't do row reduction or anything. We can just, to analyze this, we can just observe that this bottom equation here, we can solve for, say, z in terms of x. We see that z is equal to negative cx divided by d. And to solve that equation here, move the cx to the other side, divide by d, and now we can take this equality and we can substitute it in to the other equation here. And then the first equation becomes ax minus bc over dx. That's equal to 1. So we've done the substitution. We've replaced this z with negative cx over d. So this equation now becomes this equation right here. So this is just, there are a bunch of symbols going on, but we're assuming that we know A, B, C, and D. So this is just one equation, one variable. Our goal is just to solve for x. And so we can do that because we can just factor out the x. I'll just do it for you. So that becomes A minus BC over D x is equal to 1. And it'll be convenient to, write this as a single fraction, write the term in parentheses here as a single fraction. So to do that, we can, for example, multiply by the special version of 1, d over d. And so this equation right here just becomes AD minus BC all over d times x is equal to 1. And so, well, that tells us right away what x is. This tells us what x is. X is d over AD minus BC. So this is great because we found an explicit formula that tells us what the 1-1 entry is in the inverse matrix. So we have this matrix, we want to find its inverse, and this thing here is supposed to be the inverse matrix. And so we found an explicit formula that tells us what the 1-1 entry is. But now notice that if you just look right above it over here, since we know what x is, we have an explicit formula for what z is. So we can just plug that into this formula here, and we see what z is. Z becomes negative c over AD minus BC. Yay! So we've actually found the first column of the inverse matrix. We have an explicit formula for the first two entries of the inverse of a 2x2 matrix. Anyways, and then similarly, you can look at the second column of the equation whose condition we want to solve. So again, this is the condition we need, so now let's compare the second columns. And we can proceed similarly. And yeah, so we can just proceed similarly. So we get like ay plus bw is equal to 0, and we get cy plus dw is equal to 1. And we can just solve this. We can solve this. Solve similarly, or you can, for practice, you can use a different technique. Write it as a matrix and do row reduction if you want. But when you do that, you'll find that y is negative b over AD minus BC, and you'll find that w is a over AD minus BC. So I'm not doing this work for you, but you can solve the system, and that is what you'll get. And so if you put it all together, we just found explicit formulas for the 4 entries of the inverse 2x2 matrix. So here's the thing you should just memorize. So if A is A, B, C, D, then A inverse, if it exists, is given by D over AD minus BC, minus C over AD minus BC. Sorry, this is a big matrix. Minus B over AD minus BC, and A over AD minus BC. And so we typically, because we can, how do you scale a matrix? You scale all the entries. So we can rewrite this by pulling that out and just putting the matrix here. So this is the formula for A inverse. So I'll put this last one in the box. This is what you should memorize. And so, of course, this only makes sense assuming that AD minus BC is not equal to 0. Otherwise, we can't divide by AD minus BC. And so this is a formula for the inverse of a matrix A. So again, I'll rewrite that one more time. If A is A, B, C, D, then A inverse is 1 over AD minus BC times D minus B minus C.